And you are of course most welcome. This is Project Euler problem number 3. The prime factors of 1, 3, 195 are 5, 7, 13 and 29. What is the largest prime factor of the number 600,851,475,143? Okay, now there are two ways to do this. There's the ugly, horrible brute force method, or there's the much cleverer way. So, silly way first. So let's take a simpler number like 102. Let's try and find the highest prime factor of this one. So the technique here is to find the square root of this number. It's going to be roughly 10, so let's just start there, 10. Now, does 10 go into 102? No, it doesn't. So let's decrease. Let's go to 9. Does that go in? No, it doesn't. What about 8? Does 8 go into 102? No, it does not. What about 7? Does 7 go into 102? 91, 90, no it doesn't. 6, surely 6 goes into 102. 6 divided by 102 is, yes, 96, 102, I believe it's 17 times. So we have found a pair of factors for 102, and we see that 17 is a factor and 17 is prime. So let's keep that in mind, 17 there. 5 obviously doesn't go in. 4, no, that doesn't go in. 3, yes it does. 3 goes in how many times? 19 and 30, 34. So, well, 3 is prime, but it's less than 17, so we can ignore this. 2 goes in 51 times. 51 is not prime. And then, of course, we're down to 1, which goes in 102 times. So, we can see that the highest prime factor is 17. So this will form the basis of the algorithm I am about to write. So you can of course go on the internet and find a nice primality test, but since I've got SymPy installed, I'm just going to use that. From SymPy import is prime, and then from math we're going to need square root and floor. Because when we take the square root of our big number, we want to take the we want to round it down to the nearest integer. So let's take our big number, this one here, copy it in. So we'll call this n, and we'll call this another. We'll have a variable. We'll have a variable called f, which just stands for factor. It's not very Pythonic, but this is a terrible algorithm anyway, so who cares? Floor. So we'll take the square root of n and we round it down to the nearest integer, and we start our search from there. So while f is greater than 1, so we're going to find factor pairs for n, either one of which could be prime. So how exactly are we going to do this? If n does divide by f, so if n mod f is equal to 0, then we need a variable to store the highest prime factor as well. So highest equals 0 to start with. Then so if f is a factor of n, then we need to find the other half of the pair and test them both for primality. So if n mod f is equal to 0, then if n divided by f, if is prime nf and nf is bigger than highest, then we want to do highest equals nf Yeah, this is an awful, awful algorithm. What do we want to do next? Elif is prime, f on its own, and f is bigger than highest, then highest equals f, and then right at the end we'll print out highest. That should give us the correct answer, but it's going to take a couple of seconds. And this is wrong because f never decreases, so I'll put this in. F minus equals 1, so I've just got myself into an infinite loop. We'll come out of that. That's embarrassing, and we'll try that again. Whoopsie, but it does produce the correct answer in a couple of seconds. This is absolutely horrible, as I'm sure you can tell. We've got divisions here, we've got horrible bits here, we've got the same operation being performed 3 times there. We've imported SymPy just to use its isPrime function. We've got 2 imports from math. And this is fine if you've actually got SymPy installed, but if you don't, then you have to go on the internet and find a primality test. Pain in the ass, isn't it? So here's a much nicer, easier way. So let's give an example. Let's start with 110. We'll say that n equals 110. Now, this is a function known as prime factorization, and it's much, much quicker. So we start not at the square root of 110, we actually start at 2. Now, does 110 divide by 2? Yes, it does. So we'll divide it by 2. N equals 55. Now, 55 does not divide by 2. So we increment p. P goes up to 3, and n does not divide by 3. So we increment p to 4, and then up to 5. And now n does divide by 5. So p equals 5. Divide n by 5, we get 11. And then p increments through 6, 7, 8, 9, and 10, and finally comes to 11. And there we are. So we know now that the lowest prime factor of 110 is 11. It's much nicer, isn't it? And it's much nicer code as well. So n equals that, p equals 2, while n is not equal to p. We simply do this. If n mod p is equal to 0, then what do we do? N divides by p. There is another step, isn't there? Is there another step? No, there isn't. Else p plus equals 1. And then right at the end, print n or p because they'll be the same. So let's see. Yeah, same answer, and in a fraction of the time. So that is problem number 3. Okay, just as I stopped the video, I just figured out that there's a further efficiency saving we could add to this algorithm. So say we start with 110, we start dividing it by 2, then we go to 55. Now once you have divided by 2 to the point where you have an odd number, no even number will divide by it. So there's no point going to 4 or 6 or 8. So once you've gone to 2, instead of incrementing by 1 every time as we're doing here, we should just increment by 2 so you get all the odd numbers. So you go 2, 3, 5, 7, 9, so on and so forth. So just to make it slightly quicker, we could do this. If p is equal to 2, p plus equals 1, else p plus equals 2. So get rid of this, and this should produce an answer even quicker. Now you won't notice it on a relatively small number like this, but if the number had like 10,000 digits, you would notice. So that produces the same answer. So that's just an efficiency saving that I just thought of. So that's it. I'll see you next time for problem number 4.